Hi, my name is Arad from the University of Greenwich and welcome to this smart watering system with IoT and neural network project as part of the MATLAB Simulink Sustainability and Renewable Energy Challenge. I chose this project because water scarcity is a critical issue worldwide. The Food and Agriculture Organization reports that inefficient irrigation practices waste up to 60% of water meant for crops. By integrating IoT and AI, the smart watering system optimizes water usage while contributing to the growing smart agriculture market. The hardware includes a Raspberry Pi 3 Model B Plus as the system's central controller. Connected to it are multiple sensors such as soil moisture sensor, which measures the soil hydration levels, DHT22 sensor, which captures temperature and humidity data, and DH1750 light sensor, which tracks the light intensity. Then there is a 5-volt 2-channel relay, which controls the water pump, and finally there is a camera connected to the Raspberry Pi itself. The Raspberry Pi is controlled remotely through the Dataplicity terminal. To manage long-running processes, the GNU screen package is utilized. A session is created and the script is executed within it before detaching. Detaching the session ensures that the script continues to run uninterrupted even after logging out from the terminal. To verify that the watering script is running, we can check the detached session. Additionally, this session can be reattached at any time to monitor or interact with the script. As you can see, the temperature, humidity, soil moisture, and light level have been recorded. Then the valve duration has been predicted, and all this data has been sent to ThingSpeak. And the pictures have been saved locally and also in the Dropbox app. As mentioned earlier, the Raspberry Pi sends the collected sensor data alongside with the valve duration to ThingSpeak, an IoT analytics platform. ThingSpeak was chosen for its seamless integration with MATLAB, allowing for advanced data visualization and analysis. As you can see here, we have 5 fields. The first 4 are the real-world data from the sensors, the soil moisture, which was around 50% to 56, temperature, which was around 16 degrees to 21, humidity between 50% to 60%, 65%, and light, which was under 150. And then the field 5, which is the valve duration. This has been predicted by the neural network. We will cover it in a second. And it has been mainly under 1 because the plant situation was mainly ideal, so it didn't need too much watering. And also, ThingSpeak allow us to visualize more plots using MATLAB. So here we have a scatter plot of soil moisture versus valve duration. And as you can see, as the soil moisture increases, the valve duration drops, which completely makes sense. And we also have a kernel density estimation of temperature versus humidity. And it shows us that the plant has been mostly in 20 to 21 Celsius and 60% humidity. And also it has very useful widgets. And here I can just see if my soil moisture is in an ideal situation or not just in a glance. And I can even change this to modify where should the danger zone be, where should the healthy zone be, and the warning zone. Also, by going to MATLAB Analysis, we can act on this data. So here I have a script that checks for the soil moisture, and if it was in the danger zone, meaning that if it was under 30% or above 70%, it will send me an email saying that the soil moisture is too low or it's too high, and this script will be run every 6 hours using the TimeControl, and it will notify me if anything goes wrong with the system. All the images are uploaded to the Dropbox app. The way it works is that Raspberry Pi uses the refresh token to request an access key whenever the previous access key is expired. Using that access key, it uploads the picture into the Dropbox app. And as you can see, we have all the images here with their date and time. And Well, you can see how the plant grows, how the water level is increasing, and well, in the first few pictures, we expect the water to increase more than when we go towards the end, because, for example, at this point the water is enough. So when we go further, we see that it has stopped watering it. And this is the final picture, which we can see that the plant has completely grown. Machine learning models have been utilized to predict how long the valve should be on based on environmental data such as soil moisture, humidity, temperature, and light level. And this script has been used to train the models. And I have trained three different models: linear regression, random forest, and neural network. So we could choose the best one, and using visual models script, we will then visualize the output to compare them. So in this script, we start off by importing the data, defining the features and the target value, normalizing the data, and splitting it to training and test with a split of 80%, so 80% training, 20% test. And then we define so we start off by training our neural network model. We define the layers. We have two layers, so two hidden layers, one which has 64 neurons, and it's fully connected, and it's activated using the ReLU function or ReLU function. And then the second one is a fully connected layer with 32 neurons, which is also activated using ReLU function. And then the last one is for the output. And here we are training our neural network model, and so the output of this is then later used in this visualize model script. So here we are importing it and using it. But for the use in the Python script, we have to run this code to generate the ONNX format, so it can be imported into Python. And we also train the random forest, and then we save it, and then the same thing for linear regression, and we save it as well. Now we go through visualize models. Here we just compare these models so we can see which one has the best performance for our case. And so I just go ahead and run this script. So it starts by importing those models, and here are the figures. So this is the last figure, and as you can see, it's comparing the overall. It's for overall comparison of MAE and RMSE, which is mean absolute error and root mean squared error. And we can see that neural network is the least for both of these cases. Random forest being the second, and the linear regression having the worst performance. And this is basically the same thing but in different plots for each individual error. And now we have the residual plots. So I will start off by this one. So we can see we first have the single predicted versus actual plot for each of these. This basically means that for example, these are the predicted values and these are the actual ones, and if it's on this line, it means that the model has predicted it correctly, and the closer these dots are to the line, the better the model is performing. And we can see that these dots are the closest to the line for neural network, and it's quite the same for random forest and linear regression. And then we create the residuals out of these. So residual means how far is this prediction. So for example, if the value is 1 and it has predicted 2, then there is one distance between these, so it will fall in 1. So these are basically the distances from predicted and actual. These ones as well. So Now keep this in mind and we'll go through this plot. I'll just keep that. So in this plot, I have put all these predicted versus actuals on the same plot. And this one is very important. So we have the residual distribution. So this is basically all these in the same plot and as a distribution plot. So this shows us that so the blue line is for neural network, the red line is for random forest, and the yellow line is for linear regression. And as we can see, neural networks has the highest peak, meaning that it has and it's around zero. So it had the most values that were zero. So most of them were predicted and actual were the same. So the predictions were correct, and even when they weren't correct, the predicted value wasn't too far. It was less than 0.5 away from the actual value. And then there is RF, so it has a lower peak and also a wider range, which means that the errors have been more and it had less zero residuals, meaning that there were more like errors. There were more mismatch between prediction and the actual value. And the linear regression was the worst in this case. So it had the most range. So sometimes, for example, the plant had to water 0 second, but it was watering it 1 second. So this basically means that there has been distance between prediction and actual value, sometimes -1, sometimes 1, and also it had the lowest peak, meaning that it had the least number of correct predictions. Time-lapse video has been created by merging all the pictures taken by the Raspberry Pi camera. It shows how the plant grows using the system. Thank you for watching this video. I hope you have enjoyed it. See you later.